Engineering 305, Chapter 8, Section 6. I call this superposition with cartoons. Really, this is a technique of using other people's solutions to help us in ours. And it's not as simple as it might sound, but I think it's a lot more fun. It requires a lot of creativity. The course learning objective, this is 22. We've only got a couple left. Be able to use the beam deflection and slope equations provided in table B19 to calculate beam deflections, which results from multiple forces and multiple moments. The way we do that is we use this table that is in the back of the book. It's on the study guide, and we have all of these equations that are set up all ready for us to give us the slope at one end. You can see that the slope equation is there, the deflection equation is there, depending on what load case we're looking at. And then we've got 8 of them there to choose from. And we will go through and work. We will take our situation, we'll convert it so that it fits these equations, and then we'll run with it. Now, I think you should understand there was a lot of work when we did deflection by integration. We're not really going to make that a whole lot less, a little bit less, but it requires now some different creativity. So they're different. Functionally, I guess the problem now shifts from using a lot of mathematics in a very pure way. Our problem is going to shift where at the beginning of class, I talked about matching up a load case or how a system is getting pushed or pulled or squeezed or into one of 3 basic load cases. That is axial, whether it was shear and torsion, or whether there was a moment loading taking place. And the reason I wanted us to do that was because that once we knew what type of load it was, it told us what type of equation to use. It's kind of like in biology. I really think about it as, which kingdom is this in? Is this in the plant kingdom or the animal kingdom? Because we deal with those differently. Once we know if it's plants or animals, then we can choose the correct loading situation. So if I've got axial loads, then here's my stress equation and here's my displacement equation. And this also comes from the study guide. If I've got shear loads or torsional loads, I know how to do that as well. Bending loads, they're a lot more complicated. We can still figure out our bending stress pretty easily. But if we're going to go to define deflections, displacements, we've got to go either to the integration methods with or without singularity functions, or we look at the cartoons that we're looking at now, these pictures. They look like cartoons to me. They're drawn with a crayon. So, or we could go to FEA to figure out our displacement as well. In order to do this, we have to look at, instead of now looking at plants and animals, we have to look farther down. What kind of an animal is it? Is it cold-blooded? Is it warm-blooded? And so we have to look at our beams. We've got to describe them further. We've got to look at how are they supported and how are they loaded. And then we start looking at the pictures of what other people have solved and try to figure out, is this something that somebody else has already done? And can we use that work with a little bit of modification to get us to what we need? We're going to wind up taking those other situations and we're going to use some creative thinking and pattern recognition, and then the liberal use of superposition to take one load or 2 loads and split them apart and then put the answers back together. I think the best way to demonstrate this is through examples. So I'm going to do example problem 811, which is simply supported at both ends with a distributed load and a point load. And we're going to look at 812, which is really kind of the same thing. It's a distributed load, point load on a cantilever beam, so it'll have different equations. And then I want to go back and do problem 826, which is a rather nasty problem, really. But I want to use our new techniques, and we'll decide whether we like the new techniques better or whether we like the integration method and finding boundary conditions at B to help us solve the problem from B to C, because that's what we had to do for problem 826. And I guess based on class today, I'll be posting a solution for 826 the old way too. So we'll have all of that coming. Lots of stuff to chew on. But that's it for now. Don't worry, there's more coming. More stuff to do. Hope you're doing well. See you soon. Yeah, wrong button.